moving with a constant speed, and we had derived a relation for the angular frequency, which is omega square equals something. There was some factor here, and then I, which is the Bessel function. So we had derived this times 1 minus alpha square minus n square. Okay. And so we had said that for n equals 0, is there a minus here? Can someone check? Was there a minus here? So for n equals 0, we said that omega n square is, was there a minus? So for n equals 0, omega n square was negative. So omega n square was negative for alpha greater than 1, or rather alpha less than 1. Okay, alpha less than 1, and alpha, if you recall, was k times a, where this k is the wave number of the instability mode. Okay. So the idea was that if omega n square is less than 0, so that means omega n is imaginary. So we claim that this means the flow is unstable. Okay. What we mean here is that because omega n is imaginary, so I omega n t will give you an exponentially decaying term and an exponentially increasing term in time. And so because of the exponentially increasing term in time, you have instability. Now an important point physically to think about is, what does this n equal to 0 mean? So if you recall, our perturbations were something like this here. Okay, so we had summation over n and then a minus infinity to infinity for both omega and k. So phi hat n k omega, and then the others we had r, yeah. So I k z minus omega, I k n z minus omega n t dk d omega. Actually, it's better to, yeah. And then this was summed over n. So what it means here is that, and we have e to the power I n theta. So what it means here is that when your n is 0, then your perturbations are axisymmetric. Perturbations are axisymmetric. Okay, they are not varying in theta. Basically, when n is 0, they are not varying in theta. Okay, and then for n greater than 0, we had n equal 1 and so on and so forth. So we said that 1 minus, I mean, even for n greater than 0, you could have some instability, because for instability basically we need 1 minus alpha square minus n square to be greater than 0. Okay, if this holds, then omega n square becomes negative and you have imaginary frequency. So if this holds, then you can have instability. So you can calculate what are the other limits of alpha, which is the dimensionless number Ka. Okay. So one important point to note here, which is what we are going to follow in our shear flow instability example also, is that we allowed omega to be complex, but forced k to be real. And there is absolutely no reason, mathematically there is absolutely no reason why one should do this. Okay, if you look at it, both omega and k are involved in this Fourier transform when we do the normal mode expansion. There is absolutely no reason why one should be allowed to be complex, other should be allowed to be real. Okay, and this brings us to a choice on the type of instabilities that we are looking. So you can think about it in this way. So, if k is imaginary, let us say if k is complex, or so if k is complex, then e to the let us say k is some real part plus I times imaginary part, then e to the power I k x basically becomes e to the power I k r x times e to the power minus k I x. Okay. Now, there is no reason for this k I to be negative also or positive also, and in fact, since most of you know this, that if you have an algebraic equation, then there is a chance that we will have both positive and negative, because complex roots always occur in conjugate pairs. Okay. So, there are very high chances that k I will be both plus and minus. So, in that case, what it means is, when k I is negative, when k I is negative, then the function is not necessarily growing only in time. We have not said anything about time. Okay, we have not said anything about time. The perturbations will, so perturbations will look something like, so if you plotted some norm of this phi prime, then perturbations will look like they are growing in x direction. Okay. So, you can think about it, and we will try to do a demo of this also next week, where if you have some perturbations and the flow is going from, let us say, your left to right, if the flow is going, you add some perturbations and they grow as you convect downstream, as you move downstream. If you fix your attention on a particular x location, you will see that the perturbations are just oscillating in time. Okay. So, if you allow k to be complex, then omega is purely, and again this is also not necessary, omega is usually real. Okay. So, it is a choice. Are you trying to look at an instability that is growing further downstream, or are you trying to look at an instability which is growing in time? Okay. And both of them have particular meanings. This one is called a convective instability. Okay. This is called a convective instability, where you have flow going from left to right, you add some perturbations, and as you convect yourself, or as you pay, or as you move your attention with the flow, then the perturbations increase. Okay. Material wise, you can think of it as they are growing in time, but in the Eulerian sense they are growing in the x direction. If you looked at a particular x location, then you would see perturbation to be oscillating with a constant amplitude. Amplitude will not be growing in time usually. There may be cases where both are occurring. Okay, there may be cases where both are occurring, and the other form, which is what we learnt in this example, was called the, so if this is the case, then it is convective instability, and if omega is complex, then your perturbations are basically I omega r t and then I minus omega I t. So, the perturbations are growing in time. At a fixed x location, they will be growing in time exponentially. Okay, and this is called your temporal instability. Okay, this is called your temporal instability. And there is absolutely no reason why you should pick one over the other. It is always mostly about convenience. Thinking about these temporal instability problems is easier compared to convective instability problems, because as you know that even though we are making these assumptions, for example, in this we had made an assumption that the flow is the base flow is uniform in the z direction. Okay, that is why we had introduced this form of normal mode assumption. Usually what happens is the base flows are hardly uniform in one direction. Okay, they will be slowly varying in that direction, but there will be variations. So, this gets tricky, because at every x location the perturbations are seeing a slightly different base flow. Okay. So, you have to allow for that variation as well. Now, some of you may think, oh, what about in time? At some later times the perturbations could be looking at different base flow. If a base flow is steady, then no. If your base flow is steady, then that won't be the case. Okay. Steady flows are usually more let us say steady laminar flows are usually easily achievable compared to uniform laminar flows. Okay. But there is mathematically there is absolutely no reason why you should pick one other than the other, and in this course we are going to mostly look at temporal instability, where the perturbations are growing in time. For example, the liquid column 1, if you recall the picture at the end of our lecture, then I said if you add a perturbation which looks like this, and if the wavelength is larger than the perimeter of this jet of this column, then it simply grows as it is in time. Okay. It simply grows as it is in time. Remember, you are doing this analysis in the frame of reference moving with the jet, and here you start to see pinch off, and then you start seeing formation of droplets. Okay. Usually the formation of droplets is not so easy. The moment you start seeing this kind of a pinch off, then inviscid assumption actually tends to fail. Okay. So, if you really have to calculate the shape of the drops that have been formed after instability, you have to do the viscous analysis as well, but we are not going to bother about that. Okay. So, you can think about this, that this is happening in time. These perturbations are growing in amplitude in time. Okay. There is no convective instability here. Remember, K was real for us. Okay. So, now building upon these, we are going to look at shear flow instability, perhaps the one of the most important topics in fluid dynamics, because this is exactly how most of the shear flows that you see in your real life. This is not the only mechanism, but this is one of the mechanism in by which those shear flows have become turbulent. Okay, and you will most probably only see turbulent shear flows. For example, you send a flow in a pipe. Okay, there will be some perturbations that occur, and if those perturbations have some particular wave number, and your flow through pipe has some Reynolds number above than a critical value, then those perturbations will grow and you will end up with a turbulent pipe flow. Okay. If you send a flow through a channel and the perturbations increase, then you will see a turbulent channel flow. If you have a boundary layer, and you send a laminar boundary layer over a flat plate in a wind tunnel, let us say, after some time, after some downstream length, you will see it becoming turbulent. Okay. So, shear flow instability is one of the most important topics, because it helps us study laminar to turbulent transition in shear flows. Okay. And this laminar to turbulent transition, it may seem like a very trivial thing for you, but it has huge implications when you are looking at aerodynamics and things like that. Okay. Understanding where the flow becomes turbulent. Okay. Understanding, let us say you have a flat plate or a wing or something, understanding where the flow becomes turbulent is important. In some cases you will want the flow to be turbulent, in some cases you won't, you will want the flow not to be turbulent. Okay. So, I would say if you are interested in these kind of things, then shear flow instability is an important topic, and we are going to look at that. So, we are going to say that our base flow is a unidirectional flow. So, it has a velocity only in x direction, y and z are 0. Okay. Maybe I can write it like this. So, y and z velocities are 0, x direction velocity is there, and that is also varying only in y direction. Okay. So, this is a simplest shear flow that we can understand, simplest shear flow that we can analyze. Okay. That is why we are taking it, there is no other reason. And the other thing is that what did I want to say? So, this is the simplest shear flow and unidirectional. It is unidirectional in nature, unidirectional and steady. Okay. This is not a function of time. So, is this velocity possible in an incompressible flow? Is this velocity possible in an incompressible flow? is capital U of y 0 0 possible in an incompressible flow? Why not? It is, right. It satisfies continuity equation. There's no problem with it. There's no problem with the statement that this is possible for incompressible flow. Can you achieve it practically? That's a different scenario. Okay, but mathematically there's no problem in this. And if you substitute this in momentum equations, then what will you get? Once you substitute this in momentum equations from y and z momentum equations, you will simply get del p by del y is 0 and del p by del z is 0. We are ignoring gravity. Okay, for now we are not entertaining any gravity. And from x momentum equation, you will simply get 1 by rho dp dx equals nu d2 capital U over dy square. Since capital U is just a function of y, so I am also going to denote this. So any d by dy, I will write it as nu of the base. Actually, let's forget about it. Yeah, let's just leave it here. So this is our base flow. Okay, this is our base flow, and now we follow the same procedure as we have done for our water column instability, the Rayleigh plateau instability. We follow the same procedure, and that is we add the small perturbations. So let us call the let us say the velocity is now plus epsilon times u prime, which can be a function of x, y, z and t, v prime which can be a function of x, y, z and t, and w prime which can be a function of x, y, z and t. Okay. For pressure, we will call, let us say, pressure. So here let us say this gives us base pressure P naught. Okay. P naught does not mean it is constant, P naught is a function of x, because whatever you have d2u by dy square. So P naught has to be some constant times x. So P is some P naught plus epsilon P prime, again x, y, z and t. Okay. We add the perturbations, we substitute this in our governing equations, and we will look at the x, y, the linearized equations. So first let us look at the governing the continuity equation. We have del dot u equals 0. You substitute this, you will get simply del dot u prime equals 0. Nothing fancy with continuity equation. The equation itself is linear. So if you add some perturbation to it, the perturbation will also satisfy that same equation, because your base flow already satisfies that equation. Okay. So the way to think about these things is that you have some quantity, let us say phi naught, and you are adding some perturbation phi prime. Okay. Let us say this is your system. I mean, this is very abstract way of writing things, but let us say this is your system of equations. Okay. L, where L is some differential operator, linear, nonlinear, whatever. Okay. The idea is that when you consider this, okay, remember that phi naught, the base flow variables that you have, they already satisfy your governing equations. Okay. So eventually, while you are linearizing, you should not have any term which has only base flow variables, because they will cancel out. Okay. As you will see in a moment, due to this, you will see that the base flow pressure gradient and base flow shear stress, they will cancel out. Okay, because base flow already satisfies the same governing equation that you are in which you are substituting this perturbation. Okay, so this is an important point to remember. I mean, if you practice, it becomes second nature, but it is important to I would say simplify your analysis, because if you have, while you are linearizing, if you have terms which have only base flow in them, then probably you have done something wrong. So now let us substitute these in the momentum equation. So what I am going to do first is, let us write down the x, y, z momentum equation separately. Okay. So when you substitute this u plus epsilon u prime, you will have epsilon del u prime by del t, or maybe let us do the full thing. And then we have u dot del u. So we have, let's say this is some u naught vector. So you have u naught plus epsilon u prime dot gradient of capital U plus epsilon u prime. So when I'm putting a vector, I mean the full velocity. When there is no vector, it means x velocity. Okay, please try to not get confused with this. So we have 1 by rho del by del x of p naught plus epsilon p prime equals nu del 2 by del x square of capital U plus del 2 by del y square of this guy. So I'm going to write down full steps for just this equation, so that you, I mean just this problem, so that you guys get familiar with the method. Okay, that's the only reason why I'm doing this full expansion. So what are the linear terms that you end up from, that you get from here? What are the order epsilon terms that you get from here? First of all, are there any base flow terms? Only base flow terms? Are there any base flow terms? What about this guy? What can you say about this guy? U naught dot grad capital U. U naught is this base velocity. So there is a dot product with gradient. So what can you say? Huh? Uh, which term? Exactly. So this is 0 because we have already taken assumptions which removes these terms for the base flow. Okay. So this is 0. So you end up with epsilon u prime dot this guy plus u naught dot del of u prime, and then an order epsilon square term which we don't care about. And then here you have 1 by rho dp naught over dx plus epsilon del p prime over del x, and then here you will have nu of, let's say, del 2 by del x square plus del 2 by del y square of u prime and an epsilon here plus a nu times d2 u over dy square. And now you see the point that I was trying to make, that the base state terms cancel out. These terms will cancel out. Okay, there are no base state terms that should survive, only base state terms that should not survive. They should not survive in your linearization. Okay, so we end up with equation. So we can simplify this further. Capital U is just a function of y. Okay, this u vector prime dot grad is looking something like this. This is basically u prime del by del x plus v prime del by del y plus w prime del by del z. This looks like this, but capital U, you know, is a function of y from the starting assumption. Capital U is just a function of y. So the only term that survives here is basically, so this guy, the only the simplification of this is epsilon v prime du dy. Okay. Now look at this term. U naught has just a x component. So the only simplification that you will get from here is that this is epsilon capital U del u prime by del x. Okay. This remains as it is, this remains as it is. So the x momentum equation, linearized x momentum equation reads something like this: del u prime over del t plus capital U del u prime over del x plus v prime du dy plus 1 by rho del p prime over del x equals nu, let us write this as del square u prime. Okay. Notice the first two terms, these are very common in your shear flow stability type of problems. Basically, what does this term signify? That there is a u prime perturbation that is being convected by capital U. You can think of it like material derivative, where this u prime perturbation is traveling with the speed capital U. Okay. But that does not mean that the wave velocity or group velocity would be equal to capital U, they could be different as well. But this signifies that there is a convection of this u prime with capital U. Okay. Convection and propagation are two different things. Okay. Convection and propagation are two very different things. For example, you have zero flow inside this room, yet you can hear me. Okay. If you choose not to listen, that is your choice, but you can still hear me, right. So, the sound waves do reach you, that is propagation, that is independent of any flow that is happening in the room. Okay. If I had a flow that was happening in the room, let us say from my side to your side, then you may notice a change in frequency, the so called Doppler effect, but you will still hear me. Okay. And you will hear me, let us say with a different frequency, different wavelength or whatever. But the point I am trying to make is that convection is something that is innate of the material. It depends on the propagation is something which is innate of the material. It happens due to material properties. Convection is due to flow. Okay. So, here I am trying to highlight that there is convection happening. Okay. There is convection that is happening. There may be propagation further on top of it. So, you can't just say that convection is happening, so wave velocity is capital U. No, that is not correct. Okay. So, this is our x momentum equation. If you do the same procedure, you are going to get your y momentum equation, which looks something like this. So, you will have the same term here. Okay. And now, if you think about this guy, okay, notice this comes from this term. Instead of u prime, you will have v prime. And what about this one? Will you have something here? No, right, because capital U, this comes from this term. So, inside the gradient you do not have any base flow velocity in y direction. So, you will have just this, and then from pressure you will get del p prime over del y, and then here also you will have this guy. So, the y momentum equation after linearization would be rather simpler. Same for the z momentum equation. Okay. And we have already derived our continuity equation for perturbations. And this system of equations which you are seeing is called linearized Navier-Stokes equations. But I do not really like to give this name, because if I change the base flow, the system will look very different. Okay. This linearization was dependent on a lot of properties of the base flow. It has a velocity only in x direction, that is varying only in y direction. So, it had a lot of properties of the base flow which were responsible for this final form of these equations. If you change that, the nature of these equations will change. So, I try not to label it like this, because they will be different in different problems. Okay. So, this is our system of linear equations. These are ODEs, all of these are ODEs. Okay. Our job is again to try to convert these system of ODEs into one single sorry, all of these are PDEs, my bad. Our job is to try to convert this system of PDEs into a system of ODEs. And to do that, we are going to resort to the normal mode assumption. Okay. Before we look at normal mode assumption, what we can do is these are 4 first order in time PDEs. Okay. These are 4 first 4 PDEs. Continuity doesn't have any time in it. So what I'm going to do is I'm going to combine them in a way to get just one single equation. Let's see how we can do that. The first thing that we can do is utilize this in these 3 equations. How do we utilize the continuity equation in the momentum equations? How do we do that? So you have divergence of u prime is 0. So how do we do that? What we do is we take a del by del x of this, we take a del by del y of this, we take a del by del z of this and add them. Okay. What is going to happen is these will become 0, time terms will become 0 because you will have del by del t of this guy which is 0. Here if you see, you will have one term here. What is that going to be? U of del 2 u prime by del x square. Here you will have u of del 2 v prime by del x del y, but there will be another term du dy del v prime by del x. Here you will have capital U del w prime by del z. So from the second, the convective term, you will get capital U del by del x of del u prime by del x plus del v prime by del y plus del w prime by del z plus du dy times del v prime by del x. This is again 0. Okay, by definition of continuity, this is again 0. What do you get for pressure? Again, we are looking at incompressible flows for now. So rho is constant. What do you get for pressure? You simply get plus 1 by rho del square of p prime, Laplacian of p prime, right? There is del by del x here already, del by del y, del by del z. So you simply get a del square of p prime. Okay, what do you get on the right hand side? What will be there on the right hand side? 0, because this will be del square of again same thing, which is 0. Okay. So eventually you are left with that 1 by rho del square of p prime is minus du dy del v prime over del x. Okay. The reason I am trying to get this is because we want to convert this system of equation into one single equation. Okay. First, we are not still doing that PDE to ODE business. We are not doing any normal mode assumption. I am just trying to look at a reduced version of this, okay, or a very condensed version if you think about it, condensed version of this. So I am trying to eliminate basically pressure from these equations, okay. And now we are in a state we can substitute some pressure term that may appear in one of these equations with this guy. Now the question is how to get this kind of a pressure term. So what I am going to do is I am going to take a Laplacian of my y momentum equation. Again, all of this you think is very arbitrary in choice, and you would be right to think about that. The only reason why I am doing this is because we reach a very well celebrated equation. Okay, so I am trying to give you that equation. There is no particular reason why we are picking these mathematical steps. We could have understood instability from that system as well. So let us look at this del square. So we have del by del t of del square of v prime plus this guy. Now this will be important, capital U del v prime by del x, and here we will have del by rho 1 by rho del by del y of del square p prime, and here you will have nu of del square of del square v prime. Okay, let us first simplify this term. So we have del square of capital U del v prime by del x, that is nothing but del dot of gradient of capital U del v prime by del x. Okay, what is this gradient? What do you get for gradient? So this is del by del x of I cap, del by del y of this j cap, del by del z of this k cap. So what do you get here? So you will get u del 2 v prime over del x square I cap plus, when you take a del by del y, you will have a du dy del v prime by del x plus capital U del 2 v prime over del y square, this whole j cap, and then you will have a capital U del 2 v prime, this will be del x del y, del 2 v prime by del x del z k cap. Okay, and now you have to take a divergence of this. So the divergence of this simply becomes this is going to be differentiated in y again. So you will have a d2u over dy square del v prime over del x plus du dy del 2 v prime over del x del y, and then we have a d by dy of this. Again, as you can think about it, it's very laborious, all of these derivations, but it is important to do them to reach a particular result. Okay, sure, del x del y. So du dy plus capital U del 3 v prime over del x del y square, and then finally we have del x del z square. Okay, this is what we get from this term. Okay, and if you look at this, these two are same, so I can just rub one off and write 2 times this guy. Okay, we are going somewhere with all of this algebra. Just hang on a second. So now we have to substitute this 1 by rho del by del y of del square p prime. Okay, del square p prime I can substitute, just take a del by del y of this term. Okay, so what do you get? So del by del y of del square p prime is nothing but, there's a 1 by rho also, from here minus del by del y du dy del v prime over del x, and that becomes minus d2u over dy square del v prime by del x minus du dy del 2 v prime over del x del y. Yeah. Is this something I missed? So now let us substitute these. Let us substitute these in the linearized beam momentum equation. Okay, let us do the substitution in this guy. So we have del by del t of del square v prime, that is there, plus this long term. Is there a way to simplify this long term? That's what I'm trying to think. Yeah, okay. So you see that this is capital U del by del x times del square v prime. Okay. If you look at these terms, these three terms, you can take capital U del by del x outside and write it as a again Laplacian of del square v prime. Okay, that is there, and then you have this d2u over dy square del v prime over del x, and then a plus 2 times du dy del 2 v prime over del x del y. and then we have a minus. So, from this pressure term we have a minus d2u over dy square del v prime over del x, and then a minus du by dy del 2 v prime over del x del y. Okay, I have substituted for these two guys. This equal to nu del square of del square v prime. I think I made some mistake somewhere. I have a feeling. Because this is not the final result. Can anyone spot any algebraic mistake? So we took the Laplacian of this equation. This term is fine. Then we have del square of this guy. So when I take gradient of this guy, and then we take a divergence of this guy, can anyone spot any mistake? Can anyone spot a mistake? So this term is fine, and then we have a 2 times du dy del by del y of del v prime by del x. Okay. Is there a term that we are I think del square p prime has a problem. I have a feeling when we take the Laplacian of these, the divergence of these and add them, I think there is a problem. Oh, we missed this term, right? We missed this term. Yes. Okay. Now things are falling into place. So please correct this. When we took the divergence, when we did this step, okay, we missed this term. So there was another term that we should have written here, and that was the same guy del v prime over del x. Okay. So this will become 2 times this guy. Okay, now things are falling into place. So there will be a 2 times here. Okay. And so you have this 2 times, and then we have these guys cancelling out and one of them cancelling out, and we are left with an equation only in v prime, and that is del by del t plus capital U del by del x of del square v prime minus d2u over dy square del v prime over del x equals nu del square of del square v prime. And this is a very standard result in shear flow instability. That is why I did all of this algebra, and this is called Orr-Sommerfeld equation. Okay. Okay. And whenever you are looking at any hydrodynamic stability textbook or the introductory textbooks for advanced fluid mechanics, you will see any stability chapter, any stability discussion, giving this result, the Orr-Sommerfeld equation. There are multiple ways to derive this equation, by the way. I have derived this equation only in V prime. You can derive the same equation in terms of stream function psi prime. Okay. The aim is to utilize continuity to eliminate pressure. Okay. So, whenever it is about utilizing continuity, you can think about it directly that you could have done it from stream function point of view, because the definition, by definition, stream function helps you eliminate continuity, but you can do it in 2D only. Okay. This is full 3D, that is why I have chosen V prime as my variable instead of stream function, because if I chose stream function, then it could have been only in 2D. I could have done it only in 2D. Okay. So, this is called your Orr-Sommerfeld equation. And now we are going to do the, so this is again a linearized PDE, and now we are going to do the normal mode assumption business and convert this into a system of ODEs. Okay. Maybe I can get rid of this part. Yeah, this part I can get. And now we substitute the normal mode assumption, that is this V prime is basically, so which are the two homogeneous directions? Which are the homogeneous directions in this kind of a base flow? What are the two homogeneous directions? So, first of all, can y be a homogeneous direction? Does y satisfy the conditions that we needed for homogeneous direction? No, right? And you can intuitively think about it as well, that if you have a base flow where velocity is varying in y, there has to be some kind of a boundary which is causing this variation. There has to be somewhere a wall that is causing a variation or something like that. Okay, either a wall, or let's say you have looked at jets and things like that. There has to be some variation. If you have variation in y, there has to be some shear involved somehow. Okay, so that is technically not a homogeneous direction. And the other obvious thing is that the flow is not homogeneous in y direction. So, y is not a homogeneous direction. The other two homogeneous directions are only x and z. Your flow is not varying in x, neither it is varying in z. So, that is our homogeneous direction. And of course, we have the time also. So, we have, so all of three integrals have the limit v minus infinity to infinity, and then we put v hat k, let us call it as kx, and then we have a kz, and then we have a y and omega e to the power I kxx plus kzz minus omega t dkx dky d omega, and this is our normal mode assumption. Okay, this is our normal mode assumption. It simplifies our this thing a lot, because del v prime by del t will be the same integral minus I omega v hat times the same thing and the same differential elements dkx dy d omega. Same for all other derivatives, you can do it in terms of this ikx, ikz and omega t. Okay. So, that means this del square operator becomes, the del square operator basically becomes d2 by dy square minus kx square minus kz square. Okay. I have put a triple sign here, basically usually it is given for definition, but what I am trying to tell you is that you can replace wherever you see del square with this guy. Okay. Wherever you see a del by del x, you can replace it with I kx times whatever, okay, whichever variable, the perturbation variable you are looking at. So, that be k d k z instead of d k y? Huh? In the integral. Yeah. Right. Yeah, you're right. Thanks. This should be dkz. Okay. And now we can substitute that here and write this. So, del by del t is replaced by minus I omega, del by del x is replaced by I kx times capital U, and then this del square is replaced by this d2 by dy square minus kx square plus kz square, all of this into v hat or operating on v hat minus d2 u over dy square. Notice that all of this normal mode assumption, this is for perturbation. Do not replace this d2 by dy square if you see something similar for the base flows with this. You are not taking Fourier transforms of the base flow, okay. You are taking Fourier transforms of the perturbations only, you are substituting that. And technically, if you really think about it, you can take the Fourier transform of this whole equation, okay. Are homogeneous directions for x for the perturbations, are homogeneous directions for perturbations are only those directions where the base flow variables will be constant. So, you can pull this thing out of the integral always, you can pull this out of the integral because this will not be a function of that direction in which you take the Fourier transform. So, that is very important. The reason why I am taking take a Fourier transform is because if you really think about this expression, this is the inverse Fourier transform expression, okay. So, you can do the inverse of the inverse and then get this result, and then we have a I kx times v hat equals nu of this d2 by dy square minus kx square plus ky square whole square v hat, okay. Let us replace this kx square plus ky square with some alpha square to make our notation easy, and let us, instead of writing d2 by dy square, let us write d square, okay. And then the final form of Orr-Sommerfeld equation is nu times d2 minus alpha square whole square equals, you can take I here common. Usually what is done is people replace this omega over kx with c, okay. This is what? This is phase velocity of the perturbations, phase velocity of perturbations in x, that is by definition of waves, okay. Omega by kx is phase velocity, d omega by dkx is group velocity. So, this omega by kx is the phase velocity in x. So, usually people will take I kx common here and you will have I kx capital U minus c times d2 minus alpha square v hat. Huh? Where? No, no. Why? Is it del by del x? So, I have written instead of del by del x, I have replaced it with ikx. Why should it be ikz?
No, instead of y, ky.
There is no ky. Where?
First one is equal to
Ah, okay. Yes. Sorry. Minus d2 u over dy square ikx v hat, okay. And usually this is how the Orr-Sommerfeld equation is presented in textbooks also. So, if you are reading the textbook and you get confused, you will see that after obtaining this, you substitute the normal mode assumption and then you get that. And look what happened when we substituted normal mode assumption. What happened? This was a, this is what, a fourth order PDE. This is del square of del square v prime, okay. This is a fourth order PDE, okay. Look what happened, we converted all of that into a fourth order ODE, okay. What you see there in the box, that is an ODE. Because of normal mode assumption, we were able to replace our derivatives in x and z by algebraic multiplications, and even due to normal mode assumption in time, we were able to replace time derivative with minus I omega term. So, we have obtained an ODE in v hat, this should be v hat here, Okay. So, how many what is the order of that ODE? What is the order of that ODE? What order ODE is that, or Sommerfeld equation? Huh? What order ODE is that? 1. So, d2 is d2 by dy square, and there is a square of this thing. So, it is a 4th order ODE. Orr-Sommerfeld equation is a 4th order ODE. How many boundary conditions do we need for this 4th order ODE? We need 4 boundary conditions. Okay. So, now we are going to look at a specific case of this simplest shear flow, and that is the channel flow. And in this channel flow, what we are going to assume is that you have two plates basically. One is at y equals plus, let us say, h by 2, one is at y equals minus h by 2. So, the gap between the channels is capital H. You know, if there is a pressure driven flow in these channels, then it has a parabolic profile. This is x, y and z. It has a parabolic profile. So, you can derive what this capital U is going to be. Okay, you can derive what this capital U is going to be. Why I am trying to get specific here is because the method of derivation of those 4 boundary conditions is actually dependent on the flow setup. Okay, what kind of a flow setup you have, based on that you will have different boundary conditions. So, here you know that U for y equals plus minus h by 2 for all x and z is 0. Okay. There is an important conclusion that we are going to make here, and then you know that V for y equals plus minus h by 2 for all x and z is 0, and same thing for W. Why is this the case? These two are true because of no slip, and this is your hard wall. Okay. But there is an interesting thing that happens. So, from here you have two boundary conditions. Okay. But there is an interesting thing that happens. So, if u at all x is 0 at some particular y, then you can also say that del u by del x at y equals plus minus h by 2 is 0. You cannot differentiate this expression in y because this is evaluated at a particular y, but you can differentiate this expression in x and z and say individually that the del u by del x and del u by del z will be 0. Del u by del z is not of much concern for us for now, but del u by del x has a lot of implications. Why? Because same thing you can say for w, and when you take the del w by del z to be 0 plus minus h by 2, then from these two what do you conclude? Del v by del y is also 0 at both the plates. And these are your additional two boundary conditions. So, you have total 4 boundary conditions for your 4th order ODE. I mean, these are in perturbations. Okay, you can write these down for perturbations basically. Okay, and then you can convert them to say that V hat equals 0 and dv hat by dy equals 0 for y equals plus minus h by 2, and now you have closed the system. Once you convert this, once you use this along with these 4 boundary conditions, you have closed the system. Okay. In our next class, we will try to see what can we derive using these conditions. Can we say something about stability? Technically, there is no way of solving this Orr-Sommerfeld equation uh, for even the simplest type of flows analytically. You have to resort to numerical techniques. We will try to have a demonstration of that numerical calculation also sometime in the lectures, but first let us discuss some analytical results that we can get. We will do that in our next lecture.